Now, I've actually done this video before and I really can't get it out of my head that we have this huge potential for tidal energy here in Victoria. And I came up with a new design for the vertical axis turbine based on Savonius's original one. Here in Australia, in the southeast corner in Victoria where we live, there's Melbourne and it's around Port Phillip Bay. Far, far over to the east is our power stations where the coal is. And these are going to come to an end soon. And we're going to rely on wind and solar and hydro. But Port Phillip Bay has this amazingly unique piece of geography about it. Sitting between Point Lonsdale on the left-hand side there and Point Nepean on the right-hand side there. So we've got the Bellarine Peninsula and the Mornington Peninsula. And in the middle is a shipping channel. This is where all the ships come in and out. The Spirit of Tasmania goes in and out on a daily basis. But there is a very unique piece of geography. Underneath this shipping channel is an amazingly deep trench. And there used to be the Yarra River used to flow through here. And on the Point Lonsdale side, it goes very shallow, right to the edge of this cliff, and then it just drops off into a 60-metre deep piece of water. When we put a piece of water over the top of it like this, you can see the shallows on the left-hand side, and then suddenly the big deep blue water there is the 60-metre trench. And on the left-hand side here of that trench is where I'm proposing to put this vertical access turbine tidal farm. And I'm particularly interested in this corner, in this sweep where the water accelerates around the corner. So flying over the ships here with Point Lonsdale in the background, we come out of the shipping channel. We're still above the trench, but we come out of the shipping channel, and this is an ideal location to be able to set up these towers. Now, in this particular design, I'm really interested in keeping the generator, the electrical component, above sea level. This can get really, really rough just here. It can also be really, really calm and beautiful at the same time. So underneath the sea, underneath the bay at this point, this is it's an intersection between the bay and Bass Strait. I want to be able to put in these towers, anchor them to the ground. They have a big shaft that comes up to a gearbox and generator on top. But I really want to anchor them away from the shipping channel, along this western edge of this cliff face here. I want to be able to design them in a way that they can be easily assembled and have really minimal impact on the ground below. I don't know what's down there. It's a national park, and being a national park, obviously building this type of structure inside of that is going to cause all sorts of problems for people. But still, nonetheless, an important thing to do with this amazing resource. But there it is on the left-hand side, the environmentally sensitive area, and we can see Port Phillip Heads Marine National Park, and you can see how shallow it is from Point Lonsdale, 1 metre, 2 metres, up to about 6 to 10 metres, and then suddenly there's this massive drop from 10 metres to 60 metres in the sheer cliff. And anyone who's ever done any boating around that area there, known as the Rip, it is a notorious piece of water when there's an outgoing tide and incoming winds from the southwest. It's a very, very treacherous piece of water, particularly on the surface where tide meets incoming sea. You end up with these horrible standing waves. So the notion of vertical access turbines has been around for a very, very long time. Savonius was around in the early 1900s. But the idea of these ones is that they go into tidal streams or into a river stream. You can see inside there's discs, and then there's this mechanism that in this particular design, this mechanism opens and closes and opens and closes to make it as efficient as possible. And turn. The idea is for it to be able to turn at very low speeds, but with a huge amount of torque. And obviously, as the tide changes its speed from the change of low and the change of high, and it sort of accelerates in between the 2 points. And this design is really designed to be able to turn at different speeds, go through a gearbox. This is a variable speed gearbox, and then keep the generators running at a constant speed. Now, of the 24 hours in a day, there's only about 16 usable hours. So we've got 4 changes of tide, 2 bottoms, 2 tops, and an hour on either side of those changes, where the tide's just not flowing enough to turn the blades. Unlike solar's really only good for about 6 to 8 hours. This would only be good for, at best, around about 16 hours. This particular design that we're looking at in between these orange discs is the turbine blades themselves. This is a very thin design, and I came up with that one really with the view of higher speed water. The water down at Port Phillip Heads doesn't flow that particularly quickly, and the idea is to go much wider. And with the wider discs, you end up with a lot more torque. So the system is designed to go slow, but with a lot more power. The orange discs that you see there, they don't necessarily need to be turning with the blades, but it is controlling any turbulent water. We want the water to be able to come through in between the discs and turn the mechanism on the inside. As you can see with a person standing there's plenty of room in here for fish to be able to move through, dolphins to be able to move, sharks to be able to move through, marine life, seaweed, all of that passes through the ingoing and outgoing currents all the time, not getting caught up in any mechanisms in here. There's gears, there's all sorts of things that I'll explain in a moment about how this thing works. But this gives us this opportunity to set them up on these big tall towers. Obviously there are different flow rates from the top of the water to the bottom of the water, different flow rates coming around near the cliff face. As I mentioned at the beginning, though, the water's about 61 meters deep here, so I want to show you what a 65 meter tower looks like. So 4 or 5 meters above water level, and then 61 meters of tower below. And this is the kind of engineering that you need to look at. It would be similar to how you would see like a big overhead crane built. This surrounding frame obviously has to be done in a steel that's going to be suitable for a marine environment. A base needs to be put in place so the thing doesn't sink, and obviously needs to be held in place with these big giant stays if we can't get good anchorage at the base of it. And you get a really good idea of the size of the thing when you see the people in scale here. So this shaft would be, as I just described, be made up of modules that just get lowered onto each other. We'd have to go and put in divers to connect all the bracing together and build this thing up in maybe 3 or 4 different stages to be able to get to the top. So from an engineering point of view, it's really challenging, and obviously you're doing this in really strong currents and unpleasant sea conditions at times. But that gives you a bit of an idea of how tall this tower is going to be. With the generator sitting on top like that, you can see the tug just for a bit of proportion there next to it. The idea of these towers is that these mechanisms that can be brought in by ship and crane and pre-assembled outside, simply lowered in place. A base goes in place, the anchorage points for the stays on the sides go in place, and then these units just get lowered down. And there might be maybe 3 or 4 of them sitting on top of each other, connected to the stays to keep them in place. So let me now explain to you the vertical axis turbine that I've redesigned.
There's a guy called Savonius came up with this concept of this shape that was what's known commonly now as a vertical axis turbine, and it works on the principle of these cups here. And you can see on my desk here I've just got a couple of crude arrows made out of tape, and the idea is that with the flow of air or water moving in this direction, it bypasses this one and it gets caught in this cup here, causing the turbine to turn around. It needs to do half a circle to complete a full cycle. So it comes all the way back around to the beginning, and of course the shape is symmetrical. Now over time, this has all been experimented with, and people have come up with different sort of locations and shapes of all of these components inside of this mechanism, and they're fixed shapes. But ideally what would happen is that you would have on one side of the turbine, of the center of the axis here, you'd have one nice big cup like that, and another cup that was offered a lot of a lot more resistance than that sort of shape there. And so this one is doing its full capture, but this one is of course much reduced, and you can get the flow of water nicely over that. And this would capture all of the water, and of course the thing would spin up to a certain point where it got around and completed its cycle, and then it doesn't work anymore unless that one was able to close and this one was able to open up. So what I've done with this concept is I've taken half of that circle there off and made it look like these two blades like that. Now when this thing is spinning around like that, that's a really efficient design. There's not a great deal of resistance just when it's spinning on its own. And so what you do is you open up this side here and you capture all the water that's moving down through here, and this blade here on this side would be nice and aerodynamic, or in my case sort of, I don't know what the word is for hydrodynamic, I suppose. And this would turn around, and then as it comes around to this side here, this has got to close and this has got to open up like that, and the cycle spins around. And so that's what I've done. I've made this creation here, and it's doing just that. So instead of the big disc on the bottom here, I've just printed up a holder, but these are the blades that I've got in the system. And you can see one opens up, and as it opens up, it closes the other side here. So what happens is, right, and we start at the very beginning of the cycle. So we have flow moving in here. So coming in and capturing. So all of this side here is capturing flow, and this is very minimal. The size of him is being completely reduced, and he's a hydrodynamic shape, and he does a couple of things. So what happens is that as the water moves through this shape and gets diverted around this way, it forces that out like so. On the other side, all the water that's hitting these blades here is forcing this thing to go around. And we get around to a point where we've gone from the starting point through 50% of its cycle, which is 90 degrees. And at 90 degrees, we've still got various shapes assisting in its propulsion around. So water's being diverted, all this water's coming down here, striking this shape here. As it strikes this shape here, it continues to assist in turning it around, and then water coming down this side here, it strikes this edge here and also contributes. But then what happens is that as it gets around to its full cycle, we're back into the position of where it was, where it wants to now go backwards, of course. But in order to go backwards, instead of going backwards, the pressure then starts to close this, and it opens this. So now we've got water striking these two faces like that, and then very, very quickly this structure is now back into its original form.
So looking at this on a larger scale, and there's all sorts of different types of scale, whether these are going to be tall, whether these are going to be wide, but this is the basic structure on a larger scale. So here's how it goes. So central shaft, these flat discs on top and the bottom, and then of course the blades get assembled. And the idea of when I printed this was the idea that it could be attached from the side instead of having to be stacked up on top. So there it is spinning around. I couldn't quite get the blades to work whilst it was spinning around to give you that idea. But this is how the blades look as they're going around. So the whole unit will actually only spin around very slowly. If you've got a 6 knot current, then that's as fast as it could ever possibly spin with the current. And the opening and closing, the way that it squeezes water in and out, also contributes to the rotational action as well. Looking down as it connects to the central drive shaft there, you can see that there's a ratcheting system. I had the thought that perhaps they could all be moving at different speeds depending on the currents. So you don't actually necessarily wanting one to be slowing down the whole process. And so if they needed to be, if you've got blades that are spinning faster than other blades, you want them to be not being dragged back effectively. So there's my idea for capturing tidal energy in this very unique piece of geography in Victoria, in Melbourne. And as we move away from coal-fired power station, this is an absolute guarantee, 4 times a day, approximately 16 hours a day of guaranteed power generation.